Okay, welcome to example 18. Before we get into that example, let me just give you a little bit of an introduction of RC circuits, also known as resistance capacitance circuits. Now up to this point, we've been only looking at circuits that involve batteries and resistors, and now we wanted to discuss what happens when we add a capacitor within a circuit that contains some resistance as well. These circuits are quite important, and there are many circuits that use this because there's that time dependence in charging the capacitor and discharging it. And what we're going to find out is that when we're charging the capacitor, the voltage and the current are not going to remain the same. So let me draw a quick little diagram to kind of give you that idea of what's happening. So what we'll find is when we close that switch, immediately that current will jump up to a peak amount, and then as the capacitor charges up, you'll find that that current will decrease exponentially as time increases and the charge on the capacitor increases, so as the capacitor becomes fully increased. So let's draw another diagram to show what's happening to the charge over time. And so what we'll find is when the switch closes, suddenly that capacitor will start to charge, and the charge on the capacitor will increase exponentially with time involved towards it. And what you'll find is it'll eventually topple off at some amount Q after T increases to infinity. So what we'll find is actually as time progresses on, the current is continuously changing and the charge on the capacitor is also changing, and there is some exponential relationship involving current initially and the current at some particular point T. Now that particular type of problem solving is involved in the AP Physics C course. What we are really only going to be studying in the Physics B course is really what happens initially and then what happens as t approaches infinity after a very, very long time. So let's discuss what happens when we start charging the circuit, and then discuss at the beginning point and at the very end point when we get t approaching infinity. So at time t equals 0, we'll initially assume the capacitor is uncharged. And so when we close the switch, completing the circuit, and we allow the current to flow around the circuit. And so everywhere in this wire, here and throughout the whole circuit, what we'll find is charge will suddenly start moving in every part of the circuit. We'll neglect the internal resistance of this battery, and we'll just consider just the EMF of the battery. And so we'll say this battery is really just an ideal battery. So at t equals 0, what we'll find is as soon as we close that switch, all right, before the switch is closed, there's no current. But as soon as we close that switch over here, then current will flow in every part of the circuit, and the current in this resistor is I. And so that I, we can call that maybe I0 if you wish, and that will be equal to the total EMF of the battery divided by this resistance R. And when the switch is closed, just when it's closed or just before it's closed, that initial charge, we can call that Q0, is 0. So there's no charge initially in the capacitor, but after a long time, that charge on the capacitor is then going to be positive Q on this plate, and then on the other plate it's going to be negative Q. Now if you think of Kirchhoff's loop rule, you can think of as you go from across the battery, you go up the EMF, then you lose that voltage IR, and then you have also the voltage across the capacitor, which is Q over C. However, as time progresses, the current I approaches 0, so this term is going to eventually go to 0, and then the EMF will be equal to Q over C. So after a long time, when that switch has been closed for a long time, the current is no longer flowing through this circuit anymore, and what we find is that the capacitor then will be assumed to be fully charged. And so we now have that formula, EMF is equal to Q divided by C. All right, if you recall, C is equal to Q over V, and we're just replacing the V with EMF. You also notice that as these two plates become charged, this plate that is connected with the negative terminal here will acquire a negative charge Q, and then this plate over here that is connected to the positive terminal of that battery will have a positive charge Q. Now we can also carry out a similar analysis for a discharging RC circuit, which I'll talk about now. So now let's say we were to remove that capacitor from the circuit and also take the same resistor and just simply actually really remove the battery out of the way and reconfigure the circuit as I've drawn over here. And if we were to discharge this, that means we're going to close this switch. So when that switch then closes, then now the capacitor acts like a battery in a sense, and it supplies energy to the circuit, though not a constant potential difference. So suddenly now the current is going to flow in the opposite direction here from positive to negative and through this resistor. You'll find that the current and the charge will also vary in time. And let me draw those graphs so you get a bit of a visual understanding of that as well. And so here I've drawn the current over time. The current will actually decrease exponentially, but you'll notice that I've drawn it on the negative axis here, or the y-axis, because now the current is flowing in the opposite direction and it's going clockwise, where earlier it was going counterclockwise. And it will, as time progresses to infinity, eventually that current will die out to zero. Now the plates that was initially charged with positive Q and negative Q will start with this initial charge, say Q0, and the charge of the capacitor will decrease exponentially as the charge discharges on the two plates and eventually approaches zero charge at infinity as well. And once again, these are both exponential functions for current and charge, and there's a relationship with that with an exponential function, but we're not going to be looking at, for example, what is the current at this particular time or the charge at that particular time. We're really only going to be interested in what happens initially when it starts to discharge and then after a very long time. And by the way, when we talk about after a very long time, we call that after steady state. So that is another way of saying after a long, long time. And going back to our current equation, the current initially when we close that switch is going to be equal to the voltage. Now that's voltage V of the capacitor divided by the resistance of the externally around the circuit here. And we could also look at that initial charge Q would be what we had initially when we charged up the capacitor. So now let's look at example number 18 and use what we just learned from this previous example, or this discussion we've been talking about, and apply it to example 18. So in this capacitance RC circuit, we have a 14 ohm resistor with a 5 microfarad capacitor and a battery with an EMF. You could think of an ideal battery with 12 volts. So what we would like to look at here is when the switch is just initially closed S. So at t equals 0. And we suddenly close this switch. Current will flow from the positive terminal towards the negative terminal. So this will go in this clockwise fashion through the circuit. All parts of this circuit will have current flowing. And what we would like to find out is what is the charge on the capacitor. And you recall C equals Q over V. So Q will be initially 0 because it's uncharged. This will be you will be using this formula later on to actually find the charge after infinity. However, there will be an initial current I. And that initial current I will be determined using Ohm's law. The total voltage will be equal to I times R. So I initially will be equal to the EMF divided by the resistance. And the EMF is 12 volts divided by 14 ohms. And that will give you a current of 8.57 amps. So initially this strong current and no charge because it's been uncharged. Now, B part. After t approaches infinity. So after a very long time, now the capacitor will be charged. And that will be equal to Q equals C times V. So that's Q is equal to 5 microfarads times the potential drop across that, which will be now 12 volts, because now there will be no potential drop over the resistor R here, because there won't be any current flowing once it's charged, and so all the potential drop will be across the capacitor now. So that will give you a charge of 60 microcoulombs. And the current will be, at that point, now 0. And that's it for example number 18.